Good morning, good afternoon, good evening, wherever you're hailing from. Welcome to a very special virtual Friday edition of the Data Services Office Hour. I am joined by my fellow Red Hatters, Karl Eklund, Sophie Watson, and Guillaume Moutier.
Yeah, you got it.
Yeah? Okay,
you
thank
got
you.
it. Yeah.
All right, I'm winning this morning. All right, kind of had a rough night here in the short household, multiple thunderstorms, lots of child holding and such. But we are here and we are ready to party, I guess. So, topic of the du jour is data engineering and data science and data engineering. Like that, to the layman here, I'll fully admit it, I'm no data nerd. Kind of means the same thing to me, but doesn't. Right? Like I get it. There's CS. There's the science behind it, then there's the engineering behind it, like the application of it. But with data, how does that like slice, I guess, as I hit my mic? Don't all jump at once.
I can start if you want, because I'm old. So that means okay. I've seen those definitions change over the past few years. So maybe we can start with that. It will help people figure out what's what and how the things are settling.
Well, let's everybody introduce yourselves first.
Sure.
Yeah, sorry. I forgot to do that. It's early. I haven't had coffee yet. But please, everybody introduce yourself. Guillaume, go ahead.
Yeah, since I have the mic, Guillaume Moutier, data engineering architect in the cloud services BU. So the title is not interesting. What's most interesting is what I do is I try to help organizations, various organizations, to set up their data science platforms, which includes data engineering, the data engineering part. So I'm here to help those people figure out the infrastructure, the applications that they have to put up, even some aspects of the project, how they want to run it, and helping them sort this out. That's what I do.
Awesome. Well, I'm Karl Eklund. I'm also an architect here at Red Hat. I have a background in academic numerical analysis. I mean, I don't always call that data science, but there's certainly data science happening in academia, right? The specific field I was focused on, it wasn't quite data science, but that's where I gained all of my interest. And then I moved into private sector and focused on technology and data strategies for enterprise surrounding data science and actually getting a return on your data science investment. So it's kind of where I'm coming from.
Awesome.
I'm Sophie Watson. I am not a data engineer, I'm a data scientist. So I'm really excited today to hear from the experts about how they work hard to make my life easier. I just want the data. I'm kind of with you, Chris, and the kind of data just happens. Data just arrives and exists, and I don't really think about how it got there. I just want to use it to, iterate through my workflow and not think about what they do. Except for this hour where we're going to learn about what they do.
Wonderful.
So, Guillaume?
Yeah, and I think it's a nice introduction. Introducing ourselves is a nice introduction to this discussion, because you see, we have different backgrounds. I have these backgrounds in infrastructure and general architecture for any organizations. Before joining Red Hat, I was the CTO of Laval University here in Canada, so also in the academics, but not from a pure data science perspective. All the other systems that you have to set up to sustain 45,000 students university. So which is much closer to a big enterprise than purely what is done inside the labs, inside the research labs at the university. So I have this background. Karl is purely academics originally, but then shifted to the enterprise world to make this happening for real into organizations. Sophie, well, she characterizes herself as a pure data scientist, but I know she's doing some data engineering, even if she doesn't want to. That's exactly the point she made, which is really important. But still, we at some point you have to do data engineering. So, what's about it? if I go back to what I was beginning to explain a few minutes ago, when I started working on those things related to data science, so let's say back 4 or 5 years ago, there was this common knowledge that a data scientist did not exist. It was described as a unicorn, because to be a data scientist, you had to know mathematics, advanced mathematics, algorithmics, and advanced statistics. Okay, these parts of academia-related area, to understand the algorithms, especially at the beginning of this deep neural network and those kind of stuff, where if you have not done 8 years of mathematics at the college, you will have struggle, maybe not understanding, but explaining or using it, it can be hard. But at the same time, you had to know a little bit about computer science, because you had to be able to program this and to enter this into the machines. And then deriving from that, you had to know how to build those machines. What would be your requirements, for processing power and storage and networking and the rest. And you also had to know about the business itself, because if you don't understand what you are trying to achieve, most of times you will prove something that the business already know, because and it's true. It's the first thing normally you learn, is that if you are trying to prove something that the organization already knows, you're just wasting your time. So there is a business goal when you, which maybe differs from academia. In academia, you will try to prove that your algorithm, that your technique is working, is producing interesting results. Okay, but in an enterprise, those results have to be useful, which is totally different. You can find something that is fantastic, but has no application whatsoever. So there's this differentiation. So back to my story 4 or 5 years ago, data scientists did not exist, but you could build a data science team, bringing all those skill sets together. Okay, some people are more versed into infrastructure and computing, some more in mathematics and everything, and the rest in business. And you had this data scientist team. For whatever reason, in my opinion, partly marketing, partly HR, partly school, the definition has shifted a little bit. And now data scientists the common acceptation will be more focused on these science aspects, algorithmics, and all those TensorFlow, PyTorch algorithm that you would use to train a model to recognize images, patterns, and data, and whatsoever. That's what would be the common description for a data scientist. But still, the rest of the work has to be done. That is gathering this data, storing the data, transforming the data, cleaning it, securing it, making it available. All those not so interesting stuff that you have to do, but still that exists. And therefore came the name to describe this, the data engineer. That's what the data engineer would do. And not only the data engineer, because after, let's say you have trained a model, you have to put it into production. That's another skill set, right, which is now coined a software engineer or ML engineer, machine learning engineer, using those models. So we have seen those, maybe it's a refinement process. Yeah. We started from, general name for this new role, this new science that emerged. And now, because it's still young, all of this is really young, 2-3 years top. Now we are seeing emerge those different categories with different skill sets and everything. And I have here, maybe I can share this very quickly. I have this image, and not even sure that's true. It's meant to challenge. Okay, right. It's part of a presentation about, as the data scientist vanished. So it's more of a challenging blog post than anything else, but it shows those different aspects of data engineering, software engineering, research, and data business analysis. So you see different aspects of the work that you have to do around this. And if I take this example, I think it's Lyft, the company, the car sharing company. They've made this change back in 2018, 19. And sorry if I'm wrong, if it's not the right company. But for example, what the position that they named data scientist back around those around those years, 2018, now is called research scientist. And people who were coined as data analysts are now called data scientists. That's just to say that those definitions are still floating and quickly evolving. So I guess it's much more interesting to focus on not the name of the role, but what's being done.
Right.
Which is data engineering. So all the things I explained, I began to explain about data processing, storing, and all those kind of things. So that's my personal view of the story. But I let Karl and Sophie come in, and because I'm sure they have another perspective on this.
No, that was an awesome intro. I can't.
I feel enlightened.
Yeah. No, I can't find anything in there that I would disagree with. I think one of the ways that I like to start conversations like this is through a story or just like a personal experience. I guess it was a couple of years ago now, probably like 5 or 6. I was working with a not-for-profit institution, and we were trying to figure out like the prospective donors, right? So how can we start to, not only regress and predict how much a donor would offer, but how do we take limited resources and our staff to like go meet with these people and, talk about like the donations and, where do we apply our resources, right, to perspectives. And what we found was as we went through this data science process, and as I looked at the data and tried to understand it and build a model and do everything with it, came to the conclusion that like I just needed more data. I mean, anyone who spends time around a data scientist is going to hear those words like the model's promising, but I need more data. And I stopped for a second. I was like, wait a second. If I had more data, in other words, donations or transactions, I wouldn't need to build a model. So it was like, it seems kind of trivial, but at that point in my career, pretty, early on, it was like kind of earth shattering. And then I started doing the research and I figured like, oh, there's a whole data strategy component to this. There's data engineering that needs to happen. You can't just take more of something and expect the end result to simply be better, right? Because in that case, more of that something would eliminate the need for modeling. So I shifted my perspective from just more data to high quality or different dimensions of data. And that's really where I view data engineering and how it fits into the puzzle.
So cleaning, sanitizing, all makes sense to me, right? Like, where do you put it? Do you just stick it in Spark? Do you throw it at a MySQL database? I mean, there's these things called data lakes and all that fun stuff, right? Like, let's cut through the, some of the terminology and get to the real, where does the data go kind of thing.
Yeah. Can we start with where does the data come from?
Yeah, that'd be great. Where does it come from?
From
and
this
then where does it
pipeline
land?
perspective, I guess it will be easier for the audience to follow. Of course, that's the first problem of the data engineer. So we're pretty agreed that the data scientists, they take the output of everything that is happening before, and they have a clean set of data that they can use. Okay, but before that, of course, you have to gather the data. And that's what Karl explained. That's what he faced at some point. Okay, where do I get this data? And how do I acquire it? So there's a whole set of solutions, software, and techniques to help you gather this data. It could be simple as plugging a sensor to your environment, and then you are harvesting the data directly from the sensor. Can be web scraping. Okay, you go every day, you go onto a web page, you scrap the latest results, I don't know, from a stock exchange or whatever, and then you play with the data. So myriads of possibilities, and each of them come with their own challenges. Do you want real-time data? Do you want to do a batch every day you are doing this web scraping? Or do you know, every year? So that's part of the refreshing thing, and that's part of the data engineering thing. But okay, let's say you have figured this out. Of course, what you have is raw data. So you have first to select what you want to use, because from the sensors data that I took as an example, maybe there are 4, 5, or 5,000 entries that the sensor is measuring, but in fact, only 2 or 3 of them are really useful. The interesting part is that you may not know it from the start, meaning that you have to be clever enough to prepare yourself, rebuilding again this pipeline, because you will start with something. Okay, I will take those 100 thing, and then I will give all those data to my data scientist, and then they will say, no, number 1 and number 10, they're heavily correlated, and in fact, it's the same data, so you can just remove number 10. Oh, you have to go back to your pipeline and then filter out number 10. And then another iteration. Oh, no, in fact, number 10 was useful because it was a little bit different. And so that's exactly what happens in the real world. And that's why it dates back from, I guess it was a survey in 2016, but nobody challenged this so far. So I guess it's the right number, but 80% of the work you are doing in data science in general is spent exactly on this, figuring out the data parts, data cleansing, aggregation, ingestion, or whatever. So you do this ingestion, then you do the cleaning, selecting the things. But of course, you maybe have to group different inputs of data. So you have some aggregation to do and refining. And finally, after some heavy work, you store it, because of course you've
invested in this data at this point. You want to save it somewhere.
Yeah, you want to save it, and you want to save it for 2 different aspects: to be able to work on it, making your inferences or or to train your models. So 2 different sorts of data storage. There is some cold storage, because maybe the data scientists, they will run their magic only next year, but still they will want to have access to the past 10 years of data. And there is another data that you want real time to be able to do the inference and everything. So different techniques so far. So that's what we would call the data lake. It's the data lake. Yes, more and more we see these named as features, because the data are features or point of interest that you can use for your model. So it's a feature store. We're evolving from this data lake thing. You put everything raw, more or less, and you figure this out, to something more refined, which is a feature store, where you have done the refining part, and then the data scientists are able to directly pick from this to do their stuff. So to your question about the tooling and everything, depending on the size of the data, you will have different solutions. Of course, if you run into big data, a few terabytes, if not petabytes of data, you definitely have to use distributed engines. All this one, MapReduce, more common now, Spark, or the new things like Starburst Galaxy, which new name for Presto, or Trino, the upstream version, but those heavily distributed query engine that will help you make this sorting out and cleaning and everything, because most of times it's lots of SQL queries. It's not that different from standard database. But one interesting thing that I've seen is that people tend to use what they know, okay, which is never a bad thing, but sometimes it's good to take a step back and think of something else. I've seen in a chat a few days ago, oh yeah, I intend to use Spark to do this, and okay, but guy, you got 500 megabytes of data. Don't bother Spark with that. You spend more.
About to say. It's like you're going to spend a lot of CPU time doing nothing.
It's kind of, Spark is great, but it's still some heavy lifting to have it tuned in the right way and everything. So maybe just append that data frame in Python is more than enough for what you want to do. And well, data scientists won't like me, but I don't care. Most of times, Excel is just perfect. Or any spreadsheet for what, depending on what you want to do. So that's what differs maybe from academics versus enterprises and things like that. It's about finding the right tool where you will just use what is necessary, but no more. Otherwise, you're spending on resources and time and implementation.
Sophie, do you do all your work in a... Yeah, I was about to say, he called you a unicorn earlier, by the way, right? Like he did give you credit for being a unicorn, but
well, no, that was the data scientists of past that knew how to do all of the things. I'm the more modern, less unicorny version, I think. But sure, it's a virtual Friday. All is well.
Right. Yeah.
So, Guillaume, when you're talking about the data engineering process there, and particularly kind of this movement towards using feature stores and the process that you were talking about, it sounded like, first off, it sounded like there was a lot of interaction with the data scientist, a lot of back and forth to determine what the data scientist needed. And that kind of led me to wonder, I feel like you're talking perhaps about a specific type of data engineering when the data scientist knows what problem they have to solve. They've already been given their task. They know what they're trying to, optimize for the business. Is there a different approach when you've just got these sensors up everywhere? No one's actually using the data yet, because that's what usually happens, right? People just collect data for data's sake.
Right.
What would you do about
it'll be useful.
that? Yeah. Do you still call that data engineering if you're just dumping it somewhere, not looking at it at all? Is that a different role?
Okay. Collecting the data is never a bad thing, because you're right, you never know what you can do with it. Okay, so that's what has been that's what has been said to the organizations for the past few years. Collect all your data. At some point, it will be useful, and I believe it's true, because with all the fantastic things happening in this domain every day, it's not even every year, it's every day that there are new techniques, new algorithms, and everything. That's fantastic. So data can always be useful. Now, for the part where you look at the data trying to find out something without any precise business goal, it comes down to business decisions. Okay, exactly like the data store. Okay, if you have the money, if you have the resources to store 10 petabytes of data a year, yeah, go ahead, do it. But it costs quite a lot of money. It's the same for data scientists. They are unicorns, so they are really rare. So you have to pay them a lot. No, not as much
Sophie
as
gets to ask
they
for a
should
raise
be
now.
paid, because it's no, I have most admiration. I'm definitely not a data scientist, and the mathematics behind this and everything, it is baffling. So I have a huge respect for data scientists. But still, if you are paying them without any precise goal, at some point you will have the CEO looking at the lines at the end of the year, say, okay, I've hired those 10 data scientists, cost me 2 million this year or whatever. What's the result? Exactly as a CEO, he would look to, okay, this factory that I've bought last year because it was a bargain, okay, what's the return on an investment? 0. Okay, let's scrap it, let's resell it or whatever. Unfortunately, in the chats in the community, I've seen this beginning to happen. Business people beginning to challenge the usefulness of having a team of data scientists. Okay, that's perfect, but what's in it for me? At the end of the day, it has to be useful. But I wouldn't say it was, in my opinion, a wrong business decision from the start. You don't start a project without any specific goal, or at least you call it a POC and it has a defined time frame. Okay, for the next 2 years, I will put a bunch of data scientists on it. If they find something useful, perfect. If not, it was an investment. As a businessman, I will start maybe 10 projects like this a year, and out of them, 2 will succeed, 2 will be so-so, and the other 6 will be just crap. That's investment. That's 101 investment. And I'm definitely not a businessman, so I won't pretend it's true, but I've managed many projects, and some projects are successful, some are not. So we are beginning to see these trends of people starting, okay, but what am I doing exactly with this? So to your point, Sophie, to your question, yeah, it's important to gather and keep as many data as you can, but in my opinion, not starting with a precise, at least business objective. I want to increase my revenue by 10%, or I want to have 10% more customers, or I want to know more about them to target my marketing campaigns, or I want to improve the overall quality in my factory. I want only 1% of defective products instead of 10% that we have now. Maybe the data science part won't resolve those things, but at least the data science team, they have a goal. They can focus on something. Okay, and it's not that different from standard science. In science, well, it happens. It happens that serendipity gives you something that you were not looking for, but most of times you have a project goal, you have a research goal. I want to cure cancer, or generally speaking, or I want to understand the interaction of this molecule with this other one. You have a goal. You just don't come in the morning and say, oh, okay, let me mix some magnesium with some other thing and see what it does. No, nobody does science like this. So you cannot expect data scientists to do the same thing in any organization. Oh, let's see what happens when I mix this data set with this data set. If you start like this, well, you're in for much disappointment. What would be your take on this, Karl? Because you've seen this for real.
Yeah, I mean, what you're describing is taking a very logical, rational, scientific process and trying to just either, use luck or pure chance or turn it into an art form. And yes, there is art as part of this, but that comes from experience, that comes from practice, that doesn't come from just willful, combining chemicals in a laboratory setting. I mean, that's very frowned upon, probably very, very dangerous as well.
Yeah, water and lithium don't mix. Magnesium is very dangerous in certain forms. Yeah, no, like
Yeah.
Basic science taught me all that. Like, don't just
Right,
throw
yeah.
random chemicals together. Things happen.
Exactly. Yeah, I think we need a PSA now. Don't mix
Yeah.
chemicals at home, people. But I want to go back to what we were talking about, the poorly scoped business definitions and the lack of a return on investment in data science, because this is something I hear all the time. I mean, all the time. I mean, we get paid to fly around the country to talk about this sort of thing, right? And to me, it doesn't make sense. And I think when we think of the diagram that Guillaume put up earlier, and there was research and data science and data engineering and data analyst, right? And that's the whole picture, right? And it's my personal opinion that a lot of people focus on the lack of a return on investment in just that data science aspect, because they're not considering all of the ancillary but required, when we look at it in this view, actions that need to be taken, right? And if you go back to thinking of my experience with low quality, insufficient data, right? If we had a robust and funded data engineering process and the models happen to not work out, right, the business is all the better for having a data foundation. I mean, that's what everything starts from, is that data foundation. And so often I would see groups say, well, let's just hire these people over here. They're data scientists. They're smart. They can do something with that data because no one else in our organization has been able to yet. Well, that's not really the right approach. So a lack of return on investment is possible. It's
possible with anything.
Not at the numbers that we see out in the community, right?
Right.
Yeah, and I think that kind of notion that data scientists will save the world.
That's all on you, Sophie.
Yeah, I mean, I don't need that kind of pressure, but also, I think this goes back into, what me and Chris Chase were talking with you about, Chris, at the last session we had. Like in our last, hour, we talked about how to integrate the work of data scientists into what application developers are doing. Right. So, I think we've seen these silos of data scientists that are off working in their own Snowflake environments. And then when you want to take the artifacts that they've created, be it a model that they've trained in a Jupyter notebook or a model that they've trained in some Python file, but we're not application developers. We don't have experience putting things into production. So when we go to put that into production, it just kind of doesn't happen and the businesses aren't seeing the return. And kind of, I think if we think about that machine learning workflow with the data scientists kind of here, and then the application developers, there's some kind of communication and pass off there. I think with the data engineering, it's just at the other end. And I don't know whether the monitor is going to be flipped as this gets streamed out to the world. So maybe my arm makes no sense at all right now, but it's kind of a timeline, right? And so I'm seeing kind of the data engineering is such a critical thing that is needed so that me and Chris can get to that point where we can put that model into production, because we need all of that data, we need that communication. And if you take any one of these people out of this arm, then you're not going to have that nice workflow that lets you put these intelligent applications into production.
This makes sense.
And that comes back to your prior questions about the link between data engineering and data science. It's a teamwork. It has to be a teamwork, because at the end of the day, you can choose to spend a few months trying to refine your algorithm to have some more efficiency or whatever, or maybe you can throw in 2 more CPUs and that's it, it works. So you see, or you can try to figure out, okay, why is my calculation taking so much time? I can tell you, because you have a crappy network, or your storage has some bottleneck or whatever. So all the things are totally intermixed, and you cannot take each and every part by itself, saying, okay, no, data engineers, you prepare the data and that's it. A data scientist, you do the calculation, and then software engineers, you put it into motion. No, it's a continuum, and all the pieces have to be integrated together because of the scenario I described at the beginning. You will have to do constant back loops to modify the data that you will ingest, and then it will, of course, modify your algorithm. Then you have to re-implement into your production systems. So it's that's a perfect example of continuous development of integration. What we have been advocating for standard development for years, it's not that it's applicable to data science, it's compulsory for data science. Mm-hmm. That's how it works. Data is constantly changing. It's even more true compared to standard applications. Let's say you have developed something to manage your finance. Well, people will still, 10 years later, people will still enter spendings or earnings, and the application itself won't change much. That's why we still have tons of COBOL lines into those banking systems and everything. It doesn't change much. Of course, it has to be adapted to regulations and some evolutions, but it's totally different from this data science where those models have to be constantly retrained from fresh data, or at least tested continuously compared to the data that is coming in, and then redeployed into production. That's a huge difference versus standard application, where I've seen in most projects you can, even if it's in agile mode, you have this waterfall process. Okay, this is the business requirements, it's fixed, finished, and then you do the development, and then you deliver it into production, and that's over. It's not true for data science. It has to stay alive. It's a continuous project, and that's really challenging for any organization.
Right. And on top of that, something I always think about with data science, which becomes more and more important, is like repeatability, traceability. So I need to, if I train a machine learning model, I need to be able to tell somebody at some point, some stakeholder or some customer, why I declined their mortgage. I need to know what data this was trained on, what day it was trained on, what hardware it was trained on. Can I reproduce that result to like the bit level reproducibility, so that we can go back and potentially advocate for the decisions that we made. Like, well, we made this decision now because of X, Y, and Z. And so for me, that I need to know exactly where my data came from, or what happened. And so I'm leaning on Guillaume and Karl to save the world.
Yeah. Team effort here, Avengers.
Yeah, we all have capes. It's true.
Nice. But Guillaume, you reminded me that I was an unfortunate data engineer at a company I used to work at, because I worked with the data scientists to help them get their data where they wanted it, to help them, run their models against it, right? Like I had to teach them a lot about building containers and about, using the AWS, what was it? Aurora, I think is what they were using. And having to go in between that, DevOps to you just need to store the data and clean the data mode was a very hard shift. And those skill sets didn't necessarily jive at the time many years ago. And, the fact that I didn't realize what I was doing was actually data engineering was probably part of the problem, right? It's just how much, I just worry about spend at that point, right? How much money do you think it's going to cost? And the business problems is what I'm worried about, as because I'm trying to run the enterprise operations, not necessarily trying to help the data scientists figure out what the problem they're trying to solve is. I was just trying to get the data to them, kind of thing. So, yeah.
Data engineering is really result-focused area, meaning you're the data plumber. Right. I don't care how you will fix how you will fix everything, but at the end you have to stop the leak, or you have to bring this water from the water heater down to the faucet. I don't know how you do it, but you have to do it. So that's why it's again, personal opinion, but it's a little bit more of a jack of all trade skill set, because you have to know some SQL. Okay, if you have a background as a DBA, that's perfect. You know this, but you also have to know some about storage, because at the end of the day, you have to store the data, and the format, the performance, and all the different techniques around that are really important. Some networking will help. If you understand the protocols, the efficiency of those protocols and everything, it will be easier to move your data around. So it's a little bit of all the things that are related to data that in my opinion makes, if not a good, at least a somewhat efficient data engineer. And that's what I see in my practice. We have started this project at Red Hat, which is called the Data Engineering Jumpstart Library, which I talked about this last time with Chris Bloom and you, Chris. It's about bringing directly usable patterns, what we call patterns, so that you can mix and match them together to create your data pipeline, which is about data engineering. So those patterns can be simple. Okay, Kafka to S3. I have some data flowing into Kafka. How do I persist them in Parquet format into object storage so that my data scientist can use it? Okay, this is a pattern that in the library we describe. We are publishing and sharing the code on how to implement that on OpenShift. That's one pattern. And we are devising many more patterns into this. So one is this one. And maybe I could quickly show you this. Just share this screen. I will make. So you see, an example of a pattern, it's trigger a Kafka event when an object is stored into my object storage. That's to create some event-driven architecture. Whenever something new is stored in my bucket, I will send information to Kafka. That's a pattern. Another one would be, okay, whenever something is happening on my Kafka bus, how do I trigger a serverless function, a knative function into my OpenShift cluster that will be able to process this event? That's another pattern, and so on. We are creating all the things in the data in the Jumpstart library, data engineering Jumpstart library. But that's the idea of mixing all those things together to be able to at the end create the pipeline, the data pipeline you need to ingest, transform, store, and make your data available. So whatever is needed in terms of skill sets to achieve this will define you as a data engineer. So that's why it's not a pure background in this or this specific thing. I've seen more and more people coming from various horizons, each with their own strength. But I guess there are some things that you cannot skip. Main one being SQL. You have to know your basics in SQL. At the end of the day, even if it's not SQL language, at least relational databases and those types of query, you will have to use them at some point in some form of another, definitely.
Awesome. And the dog agrees.
Yeah, perfect.
It's just chaos here this morning. So containers, building containers for data science. We were talking about that a little bit in the pre-show, right? Like data scientists lean on the bleeding edge of stuff. And, me as, an RHCSA or, DevOps engineer, whatever you want to call me, I'm focused on stability and resilience. So I'm going to run things like RHEL and OpenShift and, it's not necessarily the latest and greatest things, but how can data scientists consume those things in an enterprise environment? That's kind of my question. Or data engineers for that matter, because I'm sure y'all use some fancy stuff too.
Well, this is the other part. Oh, Karl, you wanted to go ahead? Yeah, please.
Yeah, go ahead. Have a stab at it, Karl.
Yeah, no, I was just going to say, what Guillaume just described, right? It's highly technical. It's unique to skills. These aren't trivial problems, right? Like, I mean, these are hard technical problems that data engineers face all the time. Same is true for data scientists, but their hard and difficult problems are slightly different, right? It's, we're talking about Bayesian statistics. We're talking about loss functions. We're talking about, tons of math. What Red Hat brings to these fields is that stability and that consistency. And there's a lot of repeatable patterns that we can do as data engineers and things that data scientists may want to start adopting from a lot of the teachings of DevOps engineers that will give us, more organization or logical patterns and that allow us to go from one model to 10, 50, 20. I mean, 100. That's the goal, is the ability to cleanly scale. Because if we have complex environments, if we have complex pipelines, if we have data scientists writing their own data engineering code that differs from the data scientist a few, cubicles away, or, streets away in their, guest bedroom, whatever. You can't just add people and expect, linear scaling, right? I mean, at some point, this will taper off unless we bring those the consistency and the patterns that, we are so good at Red Hat.
Mm-hmm.
And that's one of the first value proposition for Open Data Hub or RODES, Red Hat OpenShift Data Science. It's bringing this reproducibility because, that was the case before. It's still the case in many organizations. Data scientist is, okay, here is your PC, your laptop, whatever, and do some data science. Okay, first thing, I will install Python and I will install a bunch of libraries, and Karl will do the same on his own laptop, and Sophie will do the same on her own laptop. And at the end of the day, hey, Karl, Sophie, can you look at my model? Oh, okay, they try to load it. Oh, no, it doesn't work because I have a library version 1.2.1 and you build it with 1.2.2, which I don't have yet, doesn't work. And the end of the story. So, and again, that's generally how it works. It's this artisanal mode of doing things, everyone with his skill set and his right set of tools fine-tuned for their own way of working, which is not compatible to the industrial mode, the enterprise mode, the scale mode that we want to do. So the value proposition on the Red Hat OpenShift Data Science or Open Data Hub is to bring this reproducibility, because each and every data scientist will just spawn its environment, and it comes with the exact same installation of Jupyter, of curated and selected libraries, and all the other tools that come with it. That's one way to ensure this reproducibility, because then you have, and if you do things properly, as Sophie described, being, okay, this is the training of this model with this version of the data at this point, and there are tools to help you trace those kind of aspects, then you are able to reproduce it on the other environment, which then simplifies the job for the software engineers, because they can directly say, okay, this model was trained with these sets of libraries. So when I'm doing my package thing with GitOps and Tecton pipelines to create the container images or whatever, I know exactly which image I have to use, which libraries I have to use, and then I just fetch the model that has been used with these parameters. And this I can automate because I have the consistency, I have all the data. So sometimes we ask, okay, but I could install again Jupyter notebooks by myself. Yeah, go ahead, but that's not the that's not the problem. The problem is that you install it exactly in the same way for each of your data scientists, and that you do it fast. You cannot rely on Bob installing the laptops of everyone and doing the same thing exactly the same time. You know, quick backstory from my old times. At some point, as a project manager, I ordered a cluster of three machines, a cluster of 3 machines. Each one came configured differently. They were supposed to work in a cluster. But on the, because this I did the week after, I did the first one the week before, and then I changed this parameter. And because I'm doing that, the technician told me, I forgot to install this package. Guy, it's supposed to be a cluster. How do you? So you see, that's how it works in any organization. Shit happens. So you have to shield yourself for this. So you have to automate everything. And that's part of what we do with Red Hat OpenShift Data Science. We have automated the deployment, the libraries curation, and everything so that you have this reproducible environment that will be exactly the same now, in 6 months from now, and whatever. And you are then able, as a data scientist, to work on data science and not to figure out why this specific package doesn't work anymore with this environment because blah, blah, blah. That's the value proposition, much more than the tools themselves that are open source anyway.
Yeah, all the tools are open source.
Right. And I think, on top of that, we've talked so much about the communication that has to happen between data engineers and application developers and those data scientists. And it just makes sense to have everybody working on the same platform. If everyone's on OpenShift, it makes those communications, those sharing of work, and that reproducibility, not just between all the data scientists, but between the data scientist and app dev handoff, the data engineer and data scientist handoff. Maybe handoff is the wrong term because it's such a back and forth, but it's early here.
No, but handoffs, like we say it all the time, a handoff is, an expense. It is a transaction that occurs between, 2 entities within an organization. So it's always going to be a conversation. It's just whether you programmatically have that conversation or whether you're just setting that thing up and you need to kind of whiteboard out exactly what you need to do. It's always a discussion.
Yeah, I have a funny little aside about me creating a model and passing it off to another data scientist for some, QA, and that was our process, right? We would check each other's work, and for the longest time, I couldn't understand why my models would not build on her laptop, right? And it evaded me for an embarrassingly long time, but in that case, we were getting different answers on these models, right? It would converge for me, it wouldn't converge for her. Effectively, we're getting wildly different results, but it's not truly failing, right? And it all comes down to there are linear algebra libraries installed that most people don't know where they live on your laptop, right? And I was truncating floating points and she wasn't, like neither of us knew that, right? So, there are times where things fail and dramatic red text and, stack traces, that's a good thing, right? If you're not running containers and you don't have that consistency, you want the errors. You don't want to be stuck in this endless loop of, failing
Weirdness.
silently and confusion.
Yeah, I could see the if you're not standardizing, right? Like if you're not creating a consistent environment for people to do whatever it is they're doing with the data, then you are going to have wildly different results, which leads to a lot of confusion, which then goes into that business discussion of what am I investing in, and like creating a consistent environment to run models against, to where it's flexible enough to say like, okay, today we're just going to upgrade this version of, PyTorch and this version of Jupyter Hub and rerun everything. and consume lots of CPU in the process and churn through all the data, but you get better results potentially, right? So everybody benefits from that at that point if you can redistribute that model. And when I say model here, I mean the model of containerizing and the actual applications in use, not the data model. Sorry, Sophie.
And that's exactly why containers are so fantastic for this kind of things, because that's one way to achieve this reproducibility. It's true for many applications, but in data science it's especially true because of the mathematical aspects of those algorithms, which always have some random aspects and seeding aspects. And let's say you have the exact same data, exact same everything, but you change the version of TensorFlow you are using, but one minor revision or whatever, the result will change.
Yeah.
And even if you run the same data with the exact same thing, exact same version of the library, the results will change because of these fuzzy randomness aspects of the algorithms. So as interestingly, the things are already skewed a little bit. You don't want to pile on it and adding some more diverging aspects to what you are doing. So you have to stick with, okay, I built this. This is the container version with everything I need, and this is the truth. And then you keep it, because that's another important aspect. You have to keep it, because in 2 years from now, you may want to run the exact same thing against a new set of data, but it has to be the exact same thing. Otherwise, it won't work.
Awesome. Well, we are rolling up on top of the hour. We got about 3 minutes left. Is there anything anybody wants to share as we wrap up here? Any little thing to help that data scientist out on a virtual Friday?
Maybe a second cup of coffee.
Yes, I would need another pot of coffee, please.
Maybe what I could add is, because of what I explained at the beginning, don't focus too much on the name or the title or whatever. There's a huge divergence now in between what people are doing and the title they have and the title with which they were recruited. Try to focus on what you want to do, what you want to achieve, your skill set, because it's sure that in 6 months from now, it will be named something else. But that's why it's important to understand all those aspects. What does what? Gather the data, clean the data, make it available, feature store and things like that. And then work on the data and then package it. Whatever names you put on this, data engineering or whatever, that's not even relevant. It's the whole process. It's the team aspect. As a team of data engineers, scientists, software engineers, you have to put something into production at the end of the day. So it's if you have this clear sight and understanding of everything, that's for the best. That's the advice I would give. Don't focus too much on, oh, I'm a data engineer, I'm doing only this or this. Well, yeah,
it's a team maybe. Maybe today you're only doing that. All right, awesome show, everybody. Thank you all for joining today. Appreciate all the insights as always.
Thanks for having us, Chris.
Hey, anytime. Coming up next on the channel, I'm going to sit down with the one and only John Chapman Jr. for an episode of In the Clouds. John is an advisor to our Build DEI group, Blacks United in Leadership and Diversity, as well as the head of Red Hat IT, or director at Red Hat IT, which is by far the best IT department I've ever worked with. Like hands down, bar none, right? Like they make life easy. So it'll be an interesting discussion to see like how they do that and how they go about problem solving in that enterprise kind of scenario. So please tune in for that at 11 a.m. Eastern, 1500 UTC. And until I see you again, please stay safe out there and come back and watch us soon.